In this lecture, I would like to talk to you about orbital diagrams. Now, the Pauli Exclusion Principle is fancily worded. It says no two electrons in the same atom can have the same set of 4 quantum numbers. So this would be similar to two printers not being able to have the same IP address, or maybe 2 people not having the same social security number. I like to reword it as follows. Electrons pair up with opposite spin. Okay? So electrons pair with opposite spin. Now, you can think of the s orbital, the 1s orbital, as a bunk beds, all right? And so helium has the electron configuration 1s2. And we can describe the n and l and m and s, the 4 quantum numbers, for the 2 electrons in the helium atom, okay? So n is 1 and l is 0. That means they're both in the 1s. And m is 0 for an s orbital, remember, because the orientation for a sphere is just the sphere. And the spin could be plus 1/2 or the spin could be minus 1/2, okay? So think about how 2 kids would get into bunk beds, okay? The first would probably call top bunk, and then the second one, since the top bunk is already occupied, would take the bottom bunk, okay? So they're always going to pair up, 2 per bunk bed. One's going to be up and one's going to be down, and that's just how we want to think about electrons. So here we are. We have a 1s orbital. We just draw it as a box here. We know it's spherically shaped. An arrow pointing up is spin plus 1/2. An arrow pointing down is spin minus 1/2. And this right here, in a nutshell, is an orbital diagram. Now let's talk about Hund's rule. Hund's rule states that electrons occupy separate orbitals with the same spin before pairing up. Think about a cabin, a summer camp cabin with 3 bunk beds in it, okay? And 6 campers are going to come in there one by one as their moms kiss them and hug them in the parking lot, and they pull their roller luggage in there. The first kid's probably going to say, I call top bunk. The next kid's probably going to call top bunk for the next one, and so on, right? Now, once all the top bunks are occupied, the next kids come in and reluctantly take the bottom bunk because that's the only place available. So again, we're going to have pairing, but look at how Hund's rule works with electrons, okay? So electrons pair up, go into separate orbitals first before pairing up. The first electron, so let me back up here. The 2px and the 2py and the 2pz are 3 different degenerate equal energy resting spots or electron clouds for electrons to reside in. We normally don't write the px, py, and pz. We just group them all together as 2p, all right? So the first electron is going to call top bunk in the first bunk bed. The second electron comes in, same way, okay? They're aligning parallel with parallel spin, with identical spin, but in separate orbitals. This, in a nutshell, is Hund's rule. But if it helps you think about it, just think about the electrons going to summer camp. The third one comes in, hey, I want top bunk too. The next electron, it's now going to have to take the bottom bunk, okay? So it's going to be spin down. The next electron comes in, spin down, and the next electron spin down. Remember that you can have 2 electrons per orbital. One has to be spin up and one has to be spin down. That's the Pauli Exclusion Principle. And electrons are always going to take different orbitals and align with the same spin before they have to pair up. Now let's talk a bit about paramagnetic and diamagnetic atoms. Paramagnetic is a situation that's defined as anywhere in the orbital diagram you have at least 1 unpaired electron, okay? And diamagnetic is when all orbitals are all paired up with electrons, okay? 1 spin up, 1 spin down. So helium, for example, it has the electron configuration 1s2, and you can see how the electrons are paired there. There's no unpaired electrons. So all paired means diamagnetic, all right? On the right, we have hydrogen. The electron configuration is 1s1. There's just 1 electron in that s orbital. It doesn't have a pairing partner, so we call this atom, this element, hydrogen, to be paramagnetic because it has at least 1 unpaired electron, okay? Let's now draw the orbital diagram for oxygen. So of course you want to locate oxygen in the periodic table, You want to find out how many electrons does it have, and you want to build up the electron configuration. Okay, you've watched my previous videos, or you already know how to do that. The electron configuration is 1s2, 2s2, and 2p4. Now what we do is we draw and label one box for each s and one box with 3 compartments for each p. Okay, so we have the 1s, just a box, the 2s, just a box, and the 2p, a set of 3 boxes that are conjoined there. Okay, next what we want to do is fill the electrons in according to the Aufbau principle. We fill from left to right, and then we want to use Hund's rule when necessary, and of course the Pauli Exclusion Principle when necessary. So again, think about summer camps. We have cabin 1s, cabin 2s way up the hill, and cabin 2p way up the hill. Okay, where are the campers first going to reside? The easiest cabin to get into. Okay, so first electron comes in, spin up. Next electron, spin down. Okay, so that cabin is filled to capacity. The next orbital is available. So the next electron, spin up. The next electron is going to pair in there, spin down. Okay, now we go to the next higher energy subshell, the 2p level. The first electron is going to come in, spin up. The next electron comes in, spin up. They're all going to align the same way. They're kind of like copying each other. The next electron comes in, spin up. All right, so that's Hund's rule. Now we need one more electron because the electron configuration is 2p4 at the end. So the next electron is going to come in and have to choose any one of the 3 bunk beds on the bottom. Okay, I just chose the one on the left, but definitely draw it spin down. Sometimes you have a question that asks, what are the quantum numbers of such and such electron? So here's the electron configuration for aluminium. What are the quantum numbers for the very last electron? So it's there in the 3p block. Okay, so go back and review and think about things. So again, the 3 means that the principal quantum number is 3, so that's the n. N is equal to 3. Okay, and then the p is shorthand for L is equal to 1. That's a designation for the orbital. Okay, so that's a p orbital. And then we want to think about m. Now m, remember, just from the rules of quantum numbers, can vary from minus L to positive L. And these represent the orientations. We sometimes call them px, py, and pz. And you see, when that electron comes into this empty cabin and sees 3 bunk beds, it could choose any 6 positions. There's no one there to tell them what to do. They could pick any top bunk, any bottom bunk, okay? Now, this electron is arrow pointing up, so we know it's so-called taken the top bunk. But any of the m values is okay. It's not like these orbitals are labeled here. So m could vary from minus L to positive L, which means minus 1 to positive 1. And I just basically did eeny, meeny, miny, mo, and picked m equals 0. You could pick any value that's allowed, and you would be correct. Now, the arrow is spin equals plus 1/2 for pointing up, and the spin is equal to minus 1/2 for an arrow pointing down. Now, in the orbital diagram, it's showing clearly an arrow pointing up, so there's only one correct answer here. Spin is equal to plus 1/2. Okay? So that's how you, in a nutshell, make orbital diagrams and use the Aufbau principle, Hund's rule, and the Pauli Exclusion Principle to put these electrons in their correct spots, all snuggled nicely in their beds. Thanks for watching, and please subscribe if you found this video helpful.